Okay. Oh, I'm not seeing the slide. Let me do that again. Here. Okay, so let us get started today's lecture. So we started to talk about the classical limit of the Schrödinger field theory, which turns out to be a good description of Bose-Einstein condensate. So we had this Lagrangian. You can derive this equation of motion. And we first look at the case when chemical potential is negative, which is just a constant potential. And we basically found that there's only sort of a trivial solution. And the plane wave solution is not an exact solution, only approximate. So as far as the exact solution goes, we find only a very trivial, boring solution. And that corresponds to basically the field sitting at the origin, which corresponds to what you have been calling the vacuum state, which has no particle in it. So the zero number is this boring state. But when we actually looked at the other sign of a positive chemical potential, the situation was actually quite different. So this is a situation where you have a large number of particles despite the repelling force, because by putting a positive chemical potential, you can gain energy by putting more particles to the system. So that's how you can sustain a large number of particles in a system despite this repulsive potential. And we don't find a general solution to this equation of motion because this is non-linear. In general, that's a very difficult thing to do, even for mathematicians. And so in general, we don't have a solution, but there is a special case, actually special cases where you can find exact solutions, where you have one trivial solution, as we have before with the negative chemical potential. But now we have a non-trivial solution where psi actually has a value. And so by looking at this piece in the Lagrangian, which is the negative of the Hamiltonian, I identify last two pieces as quote unquote potential for psi. So this V is now replaced by just a number. And this piece here doesn't contain any derivative. So if you're looking at the case when psi is independent of space, which is a homogeneous solution, then the last two terms are the only thing there is. Then I plotted the last two terms as a function of psi on a complex plane. So let's say this is the real axis, this is the imaginary axis of psi. And on this complex plane, you find this potential to look like this. So this first piece is minus mu psi log of psi. That's why the potential goes down quadratically as a function of psi. And the last piece here, lambda over 2 psi log of psi log of psi psi, is a quartic positive piece. So that's why potential goes up at large field value, where quartic term dominates over the quadratic term, because higher power always dominates at large values. So that's why you find this potential. And because this is function of only the modulus of psi, this is actually rotationally symmetric on a complex plane, which is just a phase change of psi. So that's this potential we just talked about. And if you think about this trivial solution sitting at the origin, you can clearly see that this is actually unstable. And once you go to the stable point of this potential, then psi actually does have a value. So in some sense, we can discard this trivial solution psi vanishing because that's unstable. The only solution we are interested in is a stable one where psi has a value. So if you solve this equation for a fixed modulus, then psi is given by the square root of that, except that it can have an arbitrary phase. So anywhere along this bottom here is a solution to the equation of motion. So you actually have an infinite number of solutions with different phases. And if you further take a Galilean transformation of the solution we have found, so because the equation of motion is covariant under the Galilean transformation, if this is the solution in a reference frame, you can go to another reference frame and find another solution that actually takes this form of the transformation, and therefore the solution turns into this. And one of you pointed out that I omitted this arbitrary phase e to the I theta in this solution, and you're completely right. I could have put that back in, but I didn't. So this is a one solution. So there are actually infinitely many solutions of this kind. And the point here is that this is representing the motion of this system with a fixed velocity v, in this case, along the x direction. So this is the solution which is static. It doesn't have dependence on x, which means that it's not moving. This is a solution which does depend on x, but fixed phase variation, which represents basically the momentum. So this is the solution which is basically moving the whole system, which is a collection of many, many atoms together with a velocity v. So this is an interesting solution now we have found, and now we are trying to make a sense of what this solution actually means. And that's when I actually showed this video last time. And let me do this again because it was kind of fun. And I know many things about the pandemic is bad, but now that I'm giving a lecture remotely, it's very easy to switch to an animation like this one. So that's one advantage, one of the few advantages we have on online lectures. And so let me show this again. And is the sound getting across? Okay. So this is the gas of atoms at high temperature when everything is moving randomly. But as you lower the temperature, then they start to move more slowly. That's the equipartition theorem. But when particles moving slow, that means the momentum is small. And small momentum means long de Broglie wavelength in quantum mechanics. And at some point, those de Broglie wavelengths start to overlap among all these particles together. Then becomes a phase transition. That whole system of atoms start to behave like a single wave. And that is the idea for the Bose-Einstein condensate. And here you see this energy level diagram. So if you think of this energy for different momenta of individual atoms, then you have the atoms distributed among many different momentum states moving randomly. But when you actually go to a very low temperature, then system collapses down. So here, the particles occupy different momentum states, and that represents they are moving in a random way. But when you go to very, very low temperature, at the end of the day, all particles occupy the same momentum. And that's possible for the boson because single quantum state can be occupied by many particles. And that's why this is a Bose-Einstein condensate. So once all particles occupy the same quantum state, they behave as if the whole system is a single classical wave. So what it turns out to be the case is that this quantum field theory we have been talking about has a classical limit, and the classical limit actually describes the collective motion of a large number of atoms, like thousands and millions of atoms together, as if the whole system is a classical wave. So that's the really weird idea about the Bose-Einstein condensate. So from the point of view we normally take, namely that individual atom is kind of particle, then this is the highly quantum state because individual particles now collectively behave as a single, the large number of particles now start to behave as a single wave. So this is a highly quantum state of matter. But from the point of view of the writing down the field equation in quantum field theory, this is just a classical solution to the equation of motion. So this is where we see this idea of the particle wave duality, and I come back and talk about that once again. But anyway, any questions about this video, at least the idea of what's going on? So on the next slide, I explain a bit more in detail what this de Broglie wavelength means as a function of temperature and when they start to overlap, which leads to this transition to this Bose-Einstein condensate that comes up on the next slide. But any questions about this video? Oh, I see many chats here. What am I saying? I don't get what the music has to do with it, but I'm also not complaining. Yeah, that's right. That's just how bosons sound, maybe. All right. Okay, I see no questions, so let me move to the next slide then. So let me explain this, the spreading out wave. So what we are talking about is called the thermal wavelength. So the idea here is what you learn, I'm sure, in freshman physics class, that it's an equipartition theorem in a system with a finite temperature. So every degree of freedom, in this case, kinetic energy in X, Y, and Z direction, has a thermal average given by half kT. And that's the equipartition theorem. So using this, you can estimate the typical momentum of the particle. So I take this P and just take a square root by moving 2m on the other side. So 2 cancels a half. This becomes mkt. So the average momentum is basically a square root of mkt. And what du Broglie told us, and that's what you studied in quantum mechanics class, is that matter wave has a wavelength that's given by the Planck constant over the momentum. So this is the size of the wavelength. And this is what is called a du Broglie wavelength. So now we can estimate it. So let's say D is the typical interparticle distance. In interparticle distance, it can be estimated using the number density. So number density is number of particles per volume. So if you take minus 1/3 power, that's a typical distance between particles. And number density is number over the volume, right? So this is the typical interparticle distance. And the particles have this de Broglie wavelength in quantum mechanics. And this de Broglie wavelength start to overlap among particles, as you saw on this movie, when the de Broglie wavelength becomes comparable or longer than 2 pi d typical particle distances. So that actually happens only at very, very low temperature. So we have an expression for lambda over here as a function of temperature. And then you can equate this to a certain density. And if we assume that we're dealing with rather dilute gas of cold atoms, where typical particle distance is something like 1,000 angstrom, you put this D in here and equate that to lambda. And knowing what M is for a typical atom, then you can work out what temperature should be so that this is satisfied. Then you find that temperature is, nanokelvin scale. So this is an incredibly low temperature. So this is only 1 part in a billion degree above the absolute zero. So this is an incredibly low temperature, but it turns out that experimentalists can achieve this incredibly low temperature and do experiment with it and observe this Bose-Einstein condensate. So as I talked about this energy level diagram, when the temperature is high, the particles are distributed by the Boltzmann distribution on the momentum space of the px and py in this picture. And this is how the particles are distributed in momentum space. And this really follows the Boltzmann distribution. But once you start getting to a very low temperature on this nanokelvin scale, then the particles start to occupy this zero momentum space with a macroscopic number of them. So this peak at zero momentum grows further as you go to lower temperatures. Everything else starts to disappear. So this is where the condensate developed. And this experiment was done by the group of Eric, name escaped me now. Eric Wieman at the University of Colorado, and he received Nobel Prize for this work on Bose-Einstein condensate. And they used this rubidium atom. And many of these experiments uses alkali atoms. Rubidium is one of them, and it has this configuration of the electron configurations. And you have one isolated electron in the s orbital. So that means this is an alkali element. And you can trap these alkali elements in a cleverly arranged configuration of the magnetic field and laser. And then you can actually also cool it down. And I will also show you another movie on how this cooling actually works later on. And then they actually observed that the macroscopic number of particles occupy this zero momentum state. And this may not actually convince you yet that this can be described by this classical wave I mentioned earlier. And that comes next when we actually look at the interference between two condensates, where you can really see the fringe pattern as if they are just the interference between two classical waves. But at this stage, I'm showing this distribution in a momentum space and demonstrating that you have this macroscopic number of atoms occupying the zero momentum state. And that's a sign of this Bose-Einstein condensate. Okay, any questions about this slide? Is that all right? Okay, I don't see any questions. And this is where you can start doing experiment for the interference of two Bose-Einstein condensates. So the idea is that they first create this, what they call the magnetic trap. And so once you have an alkali atom, because you have one isolated, oh, I'm sorry, this is a mistake. This is 2p6 and 3s1. I'm going to correct the slide later on. So you have one isolated electron in s orbital, and an electron, of course, has a spin, and it also has a magnetic moment. So when you have a magnetic field, then you have the coupling between the magnetic moment and the magnetic field. And if the magnetic field is spatially dependent, and then this is actually kind of potential energy term for the atom. And so you can create this kind of harmonic trap using the cleverly configured magnetic field, and all the atoms accumulate at the center. But what they do in addition to it is to send a laser across this condensate that gives you this repulsive potential in the middle, so that you can separate condensates into two pieces. And that's how you can see these two different condensates. And by making this laser more powerful, then you can separate them even further. So that's the idea of what they're doing right here to create two condensates. And because of this trapping, they are sort of hanging in the air by using, again, clever configuration of laser. And laser is, again, just a combination of electric and magnetic fields. So using these magnetic fields, you can create a potential well midair so that these two condensates are hanging in the air. Then at some point, you just turn off the trapping laser, and then these two condensates start to drop just by the gravitational pull by our planet. And as they drop, they also start to expand. And after some time, they start to overlap with each other. And that's when two condensates overlap, and you expect to see the fringe pattern if they really do behave like a classical wave. And that's this picture here. So one condensate is here, another condensate is over there, and they start to overlap. Then clearly you see this fringe pattern. And remember, one condensate contains thousands of atoms. Another condensate also contains thousands of atoms. But when they overlap, you see this fringe pattern. So this is an experimental evidence that this collection of thousands of atoms behave as if it is a classical wave. And that's the idea of Bose-Einstein condensate. And that can be described by the wave I mentioned earlier by looking at the Euler-Lagrange equation in quantum field theory. So quantum field theory is something we build up, trying to describe particles, especially multi-particle systems, and we arrived at the Schrödinger Lagrangian. But now we can use Schrödinger Lagrangian and treat it as if it were a classical wave of some sort. And that actually turns out to be a good description of this system with thousands of atoms behaving collectively together. And that's the idea of the Bose-Einstein condensate. Okay, and let me pause here and see if there are any questions, either on this slide or on that slide. No? You guys are kind of quiet today. Are you sure? No questions?
Nope. Actually, I do have a question.
Go ahead, Natalie.
It's on the very beginning slide. Okay, this might be a silly question, but
no question.
In the Euler-Lagrange equation, in the Euler-Lagrange equation that you gave for the special case,
just one. So you're talking about solutions for the special case, okay?
Yeah. So where exactly does temperature come into play for that?
So when you're solving this equation, then we are talking about the zero temperature. And there is a formalism you can use to describe the finite temperature case too, but I'm afraid that would be beyond the scope of this course. So for that purpose, we have to actually do yet another reformulation using something called the path integral, and do weird thing. You change the time to imaginary axis and make it periodic. And if you do that, you can use quantum field theory to describe the finite temperature system. And because that sounds even more bizarre than what we are doing already, so I actually postponed the discussion to some other classes you might take in the future. So I'm not doing finite temperature discussion in quantum field theory. So what we are doing here is strictly at zero temperature. And as long as temperature is zero, everything we are doing here is still correct. So I apologize that we are not doing finite temperature here, but if you stick to zero temperature, this is the right description.
It's fine. I'm really not disappointed about it.
Okay, all right. I'm glad to hear that. Okay,
Thank
any other
you.
questions? I'm not going to show this video again, but you see this link in the slides, so you can actually go ahead and download it yourself. And then I talked about thermal wavelength, at what kind of temperature they start to overlap with each other. And after they start overlap, the whole system starts to behave as if it is a single wave. And that's what you're observing here. Okay, any other questions?
How do you observe the Bose-Einstein constant condensate without heating it up too much?
Are you talking about heating up the Bose-Einstein condensate?
No, like how do you observe the Bose-Einstein condensate without adding too much energy such that it transitions out of being a Bose-Einstein condensate?
Okay, so I actually haven't looked it up. So I believe they shine light on it, and obviously that would actually heat the system up in principle. But if I remember correctly, they used a different wavelength of light so that it's not resonantly absorbed by the atom you're using, so that the energy is transferred rather minimally. And so that's how you make sure that the shining light does not heat up the system at least too much, that you can take a picture of it. But you're welcome to look at this paper, which shows more details about it. So sorry, I haven't actually looked into that detail, but I remember reading it once, understood it once, I forgot the details, but it's described in there. So please look at the paper. Sorry. Any other questions? Okay, but anyways, this is actually an incredible thing. So thousands of atoms together behave as if it were a classical wave. And so this is actually the more detailed data on this fringe pattern. So if you actually take this absorption rate of light, so again, this is meant to be a minimal amount of absorption, not to heat the system up, but looking at this absorption light, you can measure the density of atoms as a function of the position. And then here, you basically see a little bit jagged, but more or less a smooth distribution of the density. But now you see this fringe pattern where this condensate and that condensate overlap. And once you actually leave this overlap region, then you start seeing this relatively smooth distribution again. So this is clearly a fringe pattern in density of the number of particles, because you can measure that by this absorption rate of light. So this is, again, the demonstration that the thousands of particles together behave as a single classical wave. So how do we actually describe this mathematically using the field we talked about? Oh, this is just yet another data on this the fringe period. And what you can do once you see the equation, you can understand, at least at the order of magnitude level, why the fringe period turns out to be on a micron scale. And I will actually ask you to do this in the next homework problem while looking at the expression on the next slide as a classical field, how you can estimate this fringe period in a given Bose-Einstein condensate. So this work actually earned Nobel Prizes to Eric Cornell. I'm sorry, Eric Cornell, so I actually got the name wrong. And Wolfgang Ketterle and Carl Wieman, so I mixed them up. I said Eric Wieman, that was wrong. So Eric Cornell and Carl Wieman, the people who worked at Colorado, Wolfgang Ketterle was at MIT. And if you actually go back to look at this, the reference, here you see Wolfgang Ketterle as the last author. And the next, you see Kern. And this is actually our Dan Stamperkern in our department, who was a postdoc in Ketterle's group. So if I understand correctly, he is actually the one who made all these experiments happen in Ketterle's group. Unfortunately, the Nobel Prize went to the leader of the group, but he was really a major part of this Nobel Prize experiment, producing this Bose-Einstein condensate for cold atoms, the first time in history. So that's a monumental work, awarded Nobel Prize in 2001. So not too long a time ago. So how do we actually describe this mathematically? So here we found this non-trivial solution to the field equation before. And here I replace square root of mu over lambda, because what we know is that psi dag of psi was supposed to be number density. And one of you asked this question before, why does the number operator is given by the integral over psi dag of psi? The answer was that psi dag of psi was supposed to be number density. When you integrate it over space, then you find the total number. So psi dag of psi is a number density n, little n. So if you take the square root of that, the psi is supposed to be given by square root of number density, little n. But we did find that you can find this kind of a non-trivial solution to the field equation, or Euler-Lagrange equation for field psi, as a function of x and t. And again, I'll be asking you to verify that this is indeed a solution to the Euler-Lagrange equation. So you will actually check yourself that this is indeed the solution. Now, what happens if you put two of these things together? The first time squared is n1, that's the number density of the first condensate. Second term squared is n2, that's the number density of the second Bose-Einstein condensate. But you have the cross term. And cross term obviously goes like square root n1 times square root n2. And then you have to take care of this phase factor. And here I'm writing it rather sloppily. So the psi1 obviously comes with the velocity v1. Psi2 comes with velocity v2. And this is the difference between the two. So v in here is the relative velocity between two condensates. And so that appears as an argument of the cosine. And I shouldn't forget this h bar that is actually in here. And I do the same thing also for this time dependence. Again, I'm being sloppy. This piece here is the energy difference between the two. But what we are interested in here is the spatial dependence, looking for the fringe pattern. So this is the dependence all we need to look at as a function of x. And what you see here is the fringe pattern is indeed the sinusoidal, in this case cosine. And the way the fringe pattern happens goes together with m, mass of the atom, times relative velocity v between two condensates over h bar. So if you plug in these numbers, you should be able to actually understand why the fringe pattern had this few tenths of micron fringe period. And that's the way you can actually do this yourself. So this is the very perfect description of this overlapping Bose-Einstein condensates. And this is where you actually see clearly that this is not the wave functions, but rather it is actually a field. Because when you talk about the wave function, then each measurement would yield a particular position, and interference pattern emerges only after repeating many measurements, right? So if you remember this experiment, double slit experiment of a matter wave, each time you measure the electron, then it appears only at one spot. A next electron would appear at a different spot. And you keep doing this, and only after doing these experiments many times over, you start to see the interference pattern. But here, you are shining light once, and you see the interference pattern. So you are not seeing any phenomenon of the collapse of the wave function here. And that's because this psi is already a classical wave. It's not the quantum wave function, but it's a classical wave. And that's why it doesn't collapse by measuring it. It's not a probability wave. It is really a density wave of the atoms. It's also not a function of thousands of coordinates. It's function of only one x. That's a real space. If you're talking about the wave function of thousands of atoms, then your wave function should be a function of x1, x2, x3, x3000, x4056, So that's not the function we're looking at over here. So definitely this is not a wave function because of these 2 points. It's not a probability wave. We don't see the collapse of the wave function. It's really a classical wave. And second, it's a function of only single x, not thousands of x's. So I hope you see this distinction between the wave function and classical field psi. So once again, I'm repeating myself, thousands of atoms collectively behave as a single classical wave. And that's the idea of this Bose-Einstein condensate. And that actually turns out to be described basically by a coherent state once you actually use the language of the Hilbert space and operators. And I'll come back and talk about that. But let me go back to this slide to see if you have any questions. And I see many chats. Anyone getting a low hum in the background? That seems to be only for Mashit. Is everything okay? Okay, all right, good. So any questions?
Yeah, Professor, so I was wondering, so if we're saying that the psi is not a wave function, I thought we got this from a solution to the Schrodinger equation. So
not Schrodinger equation, we actually solved this non-linear Euler-Lagrange equation.
Right, okay.
This equation, which is non-linear because of the last term. And this is not a Schrodinger equation. This is the field equation that is derived from this field theory Lagrange.
Okay.
Is that okay, Chirag?
And so then wouldn't psi then be the annihilation operator?
Yeah, so this is actually an annihilation operator once you quantize it. So annihilation operator behaves as if classical wave. But that's what we have seen before. In harmonic oscillator, the annihilation operator has an expectation value, and that's the coherent state. And you looked at time evolution of the coherent state where x and p really moved as if it was a classical pendulum. So it turns out that solving classical field equation for psi is the same thing as looking for the coherent state for the harmonic oscillator. And psi having a value and moves as a function of x and t is the same idea that the classical pendulum is going back and forth. So once you have a coherent state in a quantum system, you can talk about annihilation operator as if it were a classical object, and you can solve this equation motion that lead to a classical behavior of the system. So in this case, that actually turns out to be this Bose-Einstein condensate. And that's the correspondence I was going to mention next. So you're ahead of the game, and that actually turns out to be what I'm going to talk about on the next slide. Excellent question. Any other questions? Let me try to quickly go back to that slide. Any other questions on this slide? So once again, I told you already that you are going to verify yourself that this is a non-trivial solution to the classical Euler-Lagrange equation for the Schrodinger field. And then use this expression to estimate the spacing between the fringe patterns by putting in some realistic numbers, and verify that this micron scale is the reasonable, the length scale for this fringe pattern.
I do kind of have another question.
Go ahead.
So to get our psi of x of t, we had to do like a Galilean transformation. And I think that's what gave us the expression with the cosine in there.
Right.
So if we had not done this Galilean transformation, we would not know about like these interference patterns. Or is there a way?
So Galilean
Yeah.
transformation was sort of in a quick and easy way to find new solutions. We found a solution where psi was totally constant just by looking at the bottom of this potential, right? And then once you know a solution, because the system is Galilean invariant, you can find other solutions by going to a different reference frame where you see this condensate moving. But you could have just tried to solve the field equation from the beginning, and you may happen to find the solution by just solving it brute force. So this was the quick way of finding a solution, but you might have gotten to this solution without knowing Galilean transformation.
Oh, so it's kind of like they did the experiment, saw the little wavy stuff and was like, and then just did a Galilean transformation. That's what prompted them to want to do something like that.
Well, you know, they just remove the trap and the Bose-Einstein constants start to fall just because of gravity. So then once it's falling, then it's moving. And that's why you have this MV in here. Does it make sense? Gerardo?
Yeah.
You don't sound sure. So
yeah,
you first create these two condensates hanging midair because of this various laser beam and magnetic potential and all that stuff. And you switch that off, then these two blobs of atoms start to fall. And as they fall, they also start to expand and then start to overlap. So this, the condensate is moving basically this way. That condensate is moving this way, and they start to overlap in the middle. And both of them are moving. So that corresponds to the Galilean transformed version of the original static solution because it's now moving.
Okay.
Right?
Yeah.
So,
I was looking for like a motivation as to like why did we want to do this transformation?
Yeah.
But
because
if they're both moving.
Yeah.
Okay. Okay. I can see that.
Both of them falling, but they start to overlap, which means that they are coming closer to each other. So two velocities are not completely parallel, but they are somewhat towards each other. And that's the velocity difference. There's a relative velocity between the two because of that. And the argument of cosine should be given by this relative velocity between two falling condensates.
Okay, I see that a lot better now. Yeah.
Okay, good. Natalie, you wanted to speak too? It looks like, no? Okay, all right. Any other questions? Okay, so this is where I wanted to get to this question from Chirag, that now that we're talking about the annihilation operator, namely psi, having a value, that is really similar to the situation we talked about, but I mean harmonic oscillator, namely the coherent state has somewhat well-defined A, which is this radius or modulus in a particular phase. And when you actually have this coherent state, you have to remember that there was this number phase uncertainty principle. So the coherent state shows indeed coherence, as the name suggests, namely you can see this kind of fringe pattern because you can have somewhat well-defined notion of the phase. If the phase is not well-defined, you don't expect to see the fringe pattern because fringe pattern is the difference in phases between two waves, right? And in order to have coherence, you need to have somewhat well-defined theta. But in order to have well-defined theta, you need to have uncertainty in n. So you need to sacrifice well-defined number in favor of getting well-defined phase. And that's what this number phase uncertainty principle is telling you. So what that means is that when you want to have this coherence, then you need to make the number uncertain. And when we are talking about harmonic oscillator, maybe it didn't sound too weird because you can think about linear superposition of different number eigenstates. And that's what you did in a homework problem dealing with the coherent state already. But if you're thinking about the system with atoms, all of a sudden that sounds crazy because you're saying number of atoms is now uncertain. It's not the eigenstate of the number of atoms. That sounds really crazy. Of course, when you build this system of the condensates, you put thousands of atoms into this potential well, you trap them, you cool them down, they eventually becomes condensate. You know how many atoms went in there. So the total number of atoms is definitely well defined. But the point here is that you have two condensates in this system, namely first condensate with total number N1 and second condensate with total number N2. So you know this total N. You know that for sure. So the point here is that when two condensates overlap, a single atom is not clear whether that atom belongs to the first condensate or second condensate because they overlap. So what it means is that even though the total number of atoms, you know for sure, you don't know the difference of the number of atoms between two condensates because single atom may sort of partially belong to condensate 1 or partially belong to condensate 2. So where it belongs is not clearly well defined. So you have an uncertainty in N1 minus N2. If one atom moves from condensate 1 to condensate 2, N1 minus N2 changes by 2 because N1 decreases by 1, N2 increases by 1, N1 minus N2 decreases by 2. So where the condensates overlap, this N1 minus N2 is indeed uncertain. Correspondingly, you can have rather certain relative phase theta 1 minus theta 2. So we do satisfy this number phase uncertainty principle. So in order to have this relative phase well defined so that we can study the interference pattern, you need to make N1 minus N2 uncertain. But that's exactly what happens when two condensates overlap. And that's how you can get a coherent fringe pattern as a function of the difference between the phases of two fields for condensate 1 and condensate 2. And that's a situation, as we learned from the harmonic oscillator, you can describe using the coherent state. So this is what I advertised some time ago when we talked about the coherent state in harmonic oscillator. It might have looked like an academic exercise trying to mimic the classical motion of the pendulum using the quantum language. But now we actually need it, namely that we need a coherent state to describe Bose-Einstein condensate. And because it's a coherent state, it's an eigenstate of the annihilation operator. And annihilation operator is psi in field theory. And that's why we're talking about non-zero psi, which satisfies the equation of motion. So that's how everything sort of hinged together. I hope that would make sense. And the crazy thing, though, is that now you're looking at this, the uncertain N1 and N2. If you're looking at the condensate number 1, N1 is no longer certain, which means you are talking about linear superposition of states with different number of atoms, just like what we have done with the harmonic oscillator by taking linear superposition of states with different N. So this is actually something you can do only in quantum field theory, where you have Hilbert spaces with different number of atoms in a single big Fock space. Then you can take linear superposition of states with different number of particles by summing up this way. But this is something you can never ever do in quantum mechanics because your Hilbert space has fixed number of particles built into it. Having uncertain N forces you to take linear superposition of states with different number of particles, which is possible in this big Fock space in quantum field theory. So now you are seeing a phenomena for the first time, something you cannot describe by the quantum mechanics, but you can in quantum field theory. Before we started discussion of Bose-Einstein condensate, we focused on understanding why QFT is the same thing as the quantum mechanics for a fixed number of particles. And you are verifying that for the two particle state right now in the homework problem. So that's true. QFT is equivalent to the multi-particle quantum mechanics. But at the same time, QFT is a collection of quantum mechanics of different number of particles. And given that, now you are allowed to talk about linear superposition of states with different number of particles. You can do this in quantum mechanics, but you can do this in quantum field theory. And now you see that that kind of tool is necessary to describe something you can observe in the laboratory. And Dan Stamperkern produces these BECs in the basement of Burge. So that's happening really in our physics department complex. And in order to understand what's going on in the basement of Burge, you do need quantum field theory. And that's the main idea I want to convey here. Now I see a question from Asha. Is there a maximum possible phase uncertainty distributed around the circle and thus a minimum possible number uncertainty? Well, maximum possible phase uncertainty is you don't know anything about the phase, so the uncertainty is 2 pi. And when theta is completely uncertain, that is represented by this band around this circle. And then the number is totally certain. And that's the number state we talked about going back to the harmonic oscillator. Does that answer the question, Asha?
So uncertainty in theta is 2 pi. Wouldn't the number uncertainty have to be such that when you multiply it by 2 pi, it's greater than a half? So it can't be 0?
That's an excellent question. So that also has to do with the fact that this number phase uncertainty is a little bit sort of cheating, right? So I give you already warning that this separation of n and theta doesn't make sense when n is 0. So there is a little bit of cheating going on here. Another cheating I'm doing is that theta has to be periodic. And when I define delta theta, this makes sense when theta is sort of somewhat well defined within a small range. But when theta is uncertain, then the maximum uncertainty you can have looks 2 pi. But that is not really captured by this expression where the periodicity in theta is sort of ignored from this expression. So in some sense, this number phase uncertainty principle is what makes sense when, first of all, n has to be non-zero. Otherwise, the whole thing doesn't make sense at all. And also when delta theta is somewhat smallish compared to 2 pi, which is the maximum. So you're completely right. If you take this expression literally, maximal delta theta is 2 pi. Therefore, there seems to be minimum delta n of 1/4 pi. It looks like that. But that is the consequence of the cheating we have done, namely to go from this separation of theta and n to this expression of n and theta. Here, we are not capturing the periodicity in theta anymore. Therefore, large theta actually is not really captured in this uncertainty principle. So that's a consequence of this little cheating we have been doing. But conceptually, this is still useful as long as you're talking about somewhat smallish delta theta compared to 2 pi. So this is a good tool, but not precise tool. Does that answer your question, Asha?
Yeah, thank you.
Okay. And that's what physicists do all the time. So as long as that's useful and it's practical, then we use it, even though it may not be totally rigorous or precise, unlike mathematicians who really do pay attention to rigor. So that's what distinguishes mathematicians from physicists, I guess. Any other questions?
Yes, so I guess I'm still a little confused about how solving the Euler-Lagrange equations of motion for the annihilation operator gives us a coherent state.
Yeah. So that's something I certainly have not explained very well. So if you remember the case of the harmonic oscillator in the homework problem, so expectation value of x and expectation of p for the coherent state really behaved like it was a classical pendulum, right? And you could have done this with the annihilation operator too. So that's basically just taking linear combination of x plus IP, if you take the unit of m omega h bar O B1, and A is whatever square root 2 x plus IP. So if x and p behaves like it's a classical pendulum, A basically just goes like e to the minus I omega t by adding x and IP together. And you could have obtained this just by solving the Euler-Lagrange equation for the annihilation operator, which is precisely that A dot plus I omega A is 0. So this is something you can work out by, again, taking linear combination of equation of motion for x and equation of motion for p. So by solving the equation of motion for annihilation operator A, you could have gotten the correct solution that gives you the classical pendulum behavior of both x as a real part of A and p as the imaginary part of p. So in the case of the coherent state, solving classical equation of motion turns out to be the same thing as solving for the coherent state with the correct time dependencies of the expectation values of operators.
And so, I mean, since the coherent state is an eigenstate of the annihilation operator, does that mean that the Euler-Lagrange equation of motion for the annihilation operator is equivalent to the like eigenvalue equation?
That's right.
Okay.
Specifically for coherent state.
Got it. Thanks.
And one caveat though is that in the case of a harmonic oscillator, we could solve the system exactly, and we knew everything about harmonic oscillator exactly. In the case of this, the Euler-Lagrange equation for the field, unfortunately, this is a nonlinear field equation. So we did find this special case of these solutions we could find exactly, but we don't find general solutions. We can take linear superposition of these solutions to obtain another solution because it's nonlinear. So it turns out the coherent state is a good description to the extent that the coupling among the atoms is weak, namely this lambda repulsive potential is rather small. So in that limit, we know it reduces the coherent state, but when lambda is finite, the coherent state is only approximate ground state of the system. And if you look at the lecture notes, that has much more detailed description of it, and that we can also talk about the corrections to it, and we'll come back and talk about that later. But this is just a warning I'm giving you here without getting to details right now, that the solving classical equation of motion is indeed the same thing as solving for the coherent state as a ground state of the quantum system. But to the extent this is only approximately in the limit where this repulsive interaction is small. And in the case of system with cold atoms, that is a good approximation because atoms are dilute, namely they are pretty far away from each other. So each atom doesn't disturb each other very much, which means that you can sort of ignore interactions among them. Then it's actually a pretty good approximation. And as a result, when you actually try to make this system of Bose-Einstein condensate more dense, then interactions among them start becoming important. And remember, we're talking about this incredibly cold temperature, nanokelvin. And when you actually have the gas at incredibly low temperature, you would expect it would solidify, right? That's something we know very well from water. If you go from gas, vapor, if you go cold temperature, it should become ice. So as a matter of fact, if you start to making Bose-Einstein condensate more dense, when atoms are closer to each other, at some point, it starts to solidify and you lose Bose-Einstein condensate. So you have to intentionally keep it dilute. And Bose-Einstein condensate doesn't last forever because of that. So what we are doing here is within the approximation where you can ignore interactions among them, which is a good approximation when the gas is dilute, then solving for the equation of motion turns out to be same thing as solving for the ground state of the quantum system within this approximation. And then we are using that as a way of really describing this fringe pattern when two condensates overlap. And that actually is a successful description that works. But when you actually go to a more strongly coupled system, which I do get to in a moment, which is the case of the superfluid liquid helium, then you cannot ignore interaction, and your prediction does not mesh precisely with the classical solution anymore. And I will talk about that too. Okay, so this is only a partial answer to the question right now, Chirag. We will come back and talk more about it, but I hope that is good enough for now, and so we can move on. Right? Any other questions? Okay, so let me just recap a little bit. So this is the particle wave duality. In the case of quantum mechanics, you start with a classical description of particles. You can write Lagrangian, you can write Hamiltonian, you can talk about the solution of the equation of motion. You can do all of these things in a classical mechanics. That's the Newtonian mechanics. Then we quantize it to introduce canonical commutation relation between X and P operators now. Then you describe this matter wave, which is both particle and wave at the same time. And that's what we have done in 137. What we are doing is the opposite. In quantum field theory, you start with wave. And we have seen this wave equation in the case of the Schrödinger field. And solving classical wave equation turned out to be a good description of Bose-Einstein condensate. And this looks like a very weird thing to do because Bose-Einstein condensate, from the particle point of view, is a highly quantum phenomenon where individual particles lose their identities, they all overlap and start to behave collectively as a single classical wave. This is a very highly quantum state of matter. But in quantum field theory, that is actually the starting point. That's why it sounds very strange and bizarre and unfamiliar. But if you actually grew up in nano-Kelvin world, the Bose-Einstein condensates are all around you, then describing atoms as a classical wave would be probably a natural thing for you to do. But when you actually heat up the system, then Bose-Einstein condensates start to evaporate. Then you start to see individual atoms coming outside from this classical wave. Then you get surprised. What's going on? I thought this was a classical wave, but I see particles coming out. Then you realize that you have to quantize this wave. And you have seen already multiple times that once you quantize Schrödinger field, you find particles because the field becomes an annihilation operator and its conjugate, the co-creation operator. And now you have a description of the system which is both particle and wave, but with a different starting point. So the point I'm conveying here is that whether you start with particles, as you have done in 137, or start with a wave, as we are doing here in 151, it's just for the convenience of mere mortals. We are not perfect. We have to start somewhere. Neither particle and wave is an actual description of the real system. It's an approximation anyway, but you have to start somewhere because we have limited grasp of what's going on in physics. But once you start somewhere, you can follow the process of quantization and will arrive at the correct description of the quantum system. If you start with the particles, you arrive at Schrödinger equation and you can describe the real quantum system. If you start with the wave, you quantize it, you arrive at the Fock space, again, you can describe the quantum system, either way. But what I have been telling you all along is that starting with the wave now has an advantage because this allows you to talk about superposition of states with different number of particles, which you do need for the purpose of describing BEC. Also, quantum statistics is built in. And so quantum field theory turns out to be a better description at the end of the day. And that's why quantum field theory became the hallmark of the modern physics these days. And that's why you are studying it. But I see the idea of the particle wave duality, whether you start with the particle or whether you start with the wave, it's just an approximation for mere mortal human beings to get started somewhere, actual thing is this weird object, which is both particle and wave at the same time. It's not that we don't have a good language for that because we didn't grow up with it. That's why you have to start with something we can conceive well, classical particle or classical wave. But we have to go through this process of quantization to arrive at in the end, the right description of these quantum systems. So that's the true idea of the particle wave duality, which I hope makes sense. So we're just approaching this quantum system, which we can't really describe with our language, either from one end, from particles, or from the other end, coming from classical wave. The real thing is the middle anyway. But we can start somewhere by taking either end of the thing, and then we do arrive at a correct description, but it turns out that starting with a wave turns out to be more useful way of approaching it. Okay, this is sort of the summary conceptually what we have been doing in QFT by now. Any questions about this conceptual point of particle wave duality? Is it starting to sink in? Because this is a whole new concept you didn't see in 137. Is it okay? All right. So one thing I learned recently is that actually people are doing experiments of producing Bose-Einstein condensate on International Space Station. So the International Space Station has this experiment of these cold atoms. And this is the device where the BEC is being created and operated by this astronaut. And they produced a wonderful video clip. You know, NASA being NASA, they are very good at the public relations, and I'd like to show that to you. Again, you see this link here, so you can enjoy it yourself once you download the slide.
It's kind of crazy to
Do you hear the sound?
You make something cold by shining light on it. Normally we think about shining light on something and making it hot. Laser cooling does something quite counterintuitive. It makes something cold by shining light on it. Temperature is about motion. The molecules in the air in this room are moving really fast, about 300 meters per second. If you cool down a gas, you're making the atoms and molecules move more slowly. And getting to the lowest possible temperatures, that's the extreme that we're trying to go to on Cal, and we learn something new when we go to those extremely low temperatures.
We start with atoms that are actually room temperature, even a little bit hotter than room temperature. We just have a vapor of them in a glass cell, where we use the radiation pressure from lasers to slow down atoms.
As it turns out, light pushes on stuff. We don't feel it when we walk out in the sunlight, but for something as light as an atom, the push that you can exert by shining light on the atom, in our case laser light, can be really significant.
We don't actually use two lasers, we actually use 6, so there's 2 this way, 2 vertical, 2 in and out, and so no matter which way the atom's moving, it's always moving towards one of the lasers, and that causes it to slow down and cools them down to 1,000th of a degree above absolute zero.
But eventually, to get to the temperatures that we need for Cal, we actually have to turn off the lasers. And what we do is we move the atoms so that they're held by magnetic forces.
And what we can do now is we can just adjust the magnetic field so that this trap that they're held in is not very deep. So we can make it so that the most energetic atoms just have enough energy to just move off and escape and they fly away.
We can actually pull out just the hot atoms, leaving the rest of them at a colder temperature. This is called evaporative cooling. It's essentially the same as when you blow on your coffee cup. The hottest molecules make it out of the water, and if you can constantly be blowing those away, you can cool down your coffee. And that gets us all the way down to these temperatures of microkelvin, a millionth of a degree above absolute zero.
But it turns out you can get even colder by using another really old trick called adiabatic expansion. If you take any gas and you expand it, it'll get colder.
So we're doing the same thing on a sort of small scale. We have this little small sample of atoms that are confined by magnetic fields. And what we're doing is we're reducing the strength of that magnetic field, which lets the atoms expand out something like a factor of 1,000, which causes them to cool off by a factor of 1,000.
This trick works so well, we get down to temperatures below 1 nanokelvin, 1 billionth of a degree above absolute zero. And it's being done on the Cold Atom Laboratory every day.
So now you know how to cool the system of atoms down to a nanokelvin temperature, and that's what they do actually on the International Space Station. So now, once we have this good description of Bose-Einstein condensate as a whole, being physicists, we also need to understand a little bit more details about it. Namely, once we think that solving this classical equation of motion is the same thing as looking for ground states, you start asking a question about excited states. So once you have a Bose-Einstein condensate, what are the excited states? So what we do is, again, start with this positive chemical potential, which gives you this a special case of the solutions, where psi has this value square root of mu over lambda. And here I'm dropping arbitrary phase. So I'm choosing a particular solution which corresponds to zero phase for the simplicity. And every point in this potential is basically the same thing. So I'm just choosing one particular solution over here. And only thing that you can measure is the relative phase. So absolute phase is not something you can measure anyway. So I'm just choosing the phase, absolute phase, to be zero, for just to simplify all the calculations. And now that we are thinking about excited state, we are no longer with this solution where psi is constant. So we think about a small perturbation. The psi is not exactly V, but would change from V a little bit. And I'm describing this a little bit of change by phi for the real part and chi for the imaginary part, because psi is complex, right? So all I'm doing here is to plug in this small expansion of psi in phi and chi. So phi and chi is meant to be much smaller than V as a perturbation to the system. Put that into the equation of state and find out the spectrum for phi and chi using this classical equation of motion. So that's what we do. And that's what we do anyway. For example, when you are looking for things like gravitational wave, then you first look for example, the Schwarzschild solution for a black hole. Then you take the solution first, look at the small perturbation around it, and write down the Einstein's equation for it, and look at the excitation, which is nothing but the gravitational wave. So whenever you have a classical field system, also electromagnetism, you can find a Coulomb potential for an atom. Then you find the solution to the vector potential, and you look for the small perturbation around it. And small perturbation would give you the electromagnetic wave. So that's how you can see a small fluctuation around the solution you have found. So it's the same idea. This is something you do with any field equation in a classical theory. So you did find a solution when psi is just V. So V is already known to satisfy the equation of motion. So you can forget about V. And then you expand this to the linear order in phi and chi. And when you just plug this in to this equation of motion, then this side is time derivative. V is just a constant that doesn't depend on time. So this drops out. All that remains is phi and chi time derivative. Same with the spatial derivatives. V is constant in space. So under derivative, it drops out. The only thing that remains is spatial derivative of phi and chi, which I forgot to write, I'm afraid. So this is a typo. They're supposed to be nabla squared in here. And for mu and lambda terms, once you stick in this V, mu V, lambda V cube are supposed to cancel because it's a solution at the bottom of this potential. So the only thing that remains, again, is the piece that has phi and chi in it. So from this piece, you drop V, so mu phi plus I chi, that's over here. And for this piece here, you have V to the phi squared to chi squared, V plus phi plus I chi, minus, I forgot to write, that this V piece would drop out. So VQ piece is canceled by this mu V piece. So if you just keep V only, this actually disappears from that cancellation. So the only piece that remains here is first order piece in phi and chi, second order piece, and third order piece. That's the highest order we have, highest power we have in this cubic term. And what we do is something called linearization. Drop all higher power terms in phi and chi, and just keep the linear term, hence linearization, which is a good approximation as long as phi and chi are small. So I'm ignoring phi squared or phi cubed compared to phi, because high order terms are smaller because phi is small to begin with. Then this piece here drastically simplifies, and I find the equation for the real part of psi, and I find the equation for the imaginary part. So you find the equation for chi, you find the equation for phi. And this solution equations are now linear because I dropped all the high order terms as an approximation. And because it's a linear equation, I can just go ahead and solve. And once you solve this, the linear equation doesn't fix the overall normalization, because if you find one solution, twice the solution is also solution being linear. So we don't attribute much meaning to the overall size of it. But what we can read off is what is called the dispersion relation, namely how the angular frequency, omega, and the wave vector, k, are related to each other. So from these linear equations, you can read off how you can find this angular velocity frequency as a function of the wave vector k. And of course, interpretation of this is that h bar times wave vector k is supposed to give you momentum. Now that we want to have quantum physics in it, h bar times angular frequency is the energy. Again, that's because of the quantum theory. So you find the relation how energy of the excitation is given by a function of the momentum of the excitation. And this is what is called the dispersion relation, namely the relationship between energy and momentum is something you can predict just by looking at this classical field equation. So we use classical field equation to identify the ground state of the system. And now you're using it again to look at the perturbation around the ground state to identify the excitation spectrum. And spectrum we find from these linearized equations is what is called the Bogolubov spectrum. Energy is given by p squared over 2m times 2 mu plus p squared over 2m, whole thing in a square root. One thing you immediately notice that if you ignore this chemical potential mu, then I have p squared over 2m times p squared over 2m square root. So that's p squared over 2m. So that corresponds to this familiar non-relativistic particle. Energy is p squared over 2m. But once you have this chemical potential, you have now a different spectrum. And that's what is shown here. So when momentum is small, where p squared over 2m is negligible compared to mu, square root of this is now linear in p. So energy in this inset goes linearly with momentum. So horizontal axis is the momentum or wave vector. Vertical axis is the energy or angular frequency. And they have this linear relation. But this inset is only for the small momentum region. If you look at larger momenta, then you can ignore mu relative to p squared over 2m instead. Then you start to recover the usual p squared over 2m. That's its quadratic behavior. This dashed line is the standard p squared over 2m for a free particle. This solid line is this Bogolubov spectrum. It starts linear and goes quadratic later, and that's the spectrum. And indeed, this dot is actually experimental measurements of the excitation of a Bose-Einstein condensate based by sending in a photon. Photon gets scattered, and you know what photon you send in, namely you know the energy and momentum of the photon. You measure the outgoing photon, which has the definite energy and momentum. And by using energy momentum conservation, you know how much energy and momentum photon lost by creating an excitation in Bose-Einstein condensate. And then you find for what momentum you lost, what energy you also lost. And that's this dispersion relation you can obtain experimentally to work out energy as a function of momentum or angular frequency as a function of the wave vector. So these dots are experimental measurements by an Israeli group, which follows exactly this Bogolubov spectrum, which you worked out on this slide by linearizing the classical equation of motion. So this is something you can also experimentally verify, as you saw on the next slide. And that's a very good confirmation that description really does work beyond just the condensate or its interference pattern, but even including the microscopic excitation of the Bose-Einstein condensate, which you can probe by sending a photon individually, and you're creating tiny, tiny excitation, which is microscopic, not the macroscopic interference between two condensates. But these microscopic excitations are something you can predict as well from the field theory, which turns out to agree very well with experimental measurements. So let me stop here again. I'm sure you got questions about this.
I have a question.
Go ahead, O'Reilly.
Did we get that dispersion relation from those two equations on the left of it?
That's right.
Okay. I'm just a little unclear on how exactly we went from those two equations to the dispersion relation.
Yeah. So the rough idea is that you basically replace everything by plane waves, that phi and chi go like e to the minus I omega t plus ikx. And of course, phi and chi are meant to be real. So at the end of the day, you need to take the real part of it, but at least you can just go ahead and plug in phi and chi being e to the minus omega t plus e to the ikx. And as I forgot to write nabla squared here, I forgot to write nabla squared here and there. And when nabla acts on a plane wave, that pulls out ik from the exponent. So this turns into h bar squared k squared over 2m, right? And here I have chi dot, and time derivative will pull out minus I omega from the exponent. So this turns into omega. So you start to see that omega is somehow related to h bar squared k squared over 2m. But you also need to take care of this mu and lambda somehow. So you have to do that. And if you actually put all of them together, now you have two linear equations, and all the derivatives are now given in terms of omega and k, and then solve for chi and phi. And after you actually remove the overall normalization phi and chi, you find an equation that turns into omega squared being this thing in a square root. And I just took the square root of both sides, and that's how you obtain this Bogolubov spectrum.
Okay, that's much more clear. Thank you.
Okay, yeah, sorry for the typo, and that's why it was probably a little hard to understand, but that's what the way that works. And again, I will be asking you to do that yourself in the homework problem. Okay, any other questions here? No questions? And I hope that this experiment data is really convincing that we are doing something right with the quantum field theory. So that's the reason why we're talking about it. So in addition to convince you that quantum field theory now allows you to take this linear superposition of different number of particles, and hence we can describe a Bose-Einstein condensate. But in addition, we can be quantitatively successful using quantum field theory to really understand what's going on microscopically with these Bose-Einstein condensates in terms of this Bogolubov spectrum. So that's the main purpose of showing that over here. And you can also think about different kinds of solutions. If you put this psi into this donut-shaped space, you constrain the x and y to a particular radius, then you can switch the polar coordinate, and you can ignore the motion along the radial direction. So I ignore r derivative. then everything becomes a function of theta only. And in particular, in the theta direction, it has to be periodic because it's just angular variable. So ignoring all dependence and imposing this periodicity in theta, I can come up with an exact solution to this once again. And the point here is that this theta dependence of the exact solution satisfying this periodicity is described by this integer n. That's the periodicity in theta. So namely that this theta dependence is the analog of the wave vector in this angular direction. But the momentum in angular direction then is quantized. It has to be an integer value. So then you predict that the flow of Bose-Einstein condensate in angular direction comes with an integer value of some minimum quantum. And I don't have time to go this in detail right now because I'm running out of time. But let me just show one slide so that you know what I'm talking about. Namely that in Bose-Einstein condensate, you have a quantum of circulation, namely how much you flow in angular direction comes in a quantized units. And that is given by what is called the circulation observable, which is v dot dx along this angular direction, which comes in the unit of h over m. That's the quantum unit of circulation. And that's something you can observe experimentally too. So you can have a circulation with n equal 1, n equal 2, n equal 3, and so on. And you don't find circulation in between those quantized values. And this is one example of something you might hear often in condensed matter physics these days. That's a sort of a big trendy subject, topologically protected state. Once something is described in terms of integers, because you can go from 2 to 1 continuously, becomes stable. You have to jump from 2 to 1, which is a tunneling process. Tunneling process is always suppressed. So the state with 2 becomes rather stable. You cannot gradually go to 1 because of this quantization condition. So this is yet another new concept I'm introducing. So I spend more time next week talking about this more slowly. But once you have this classical field theory as a description of the quantum, the Bose-Einstein condensate, you start to discover new phenomena of topologically protected states. So we will go through this once again, much more slowly. So don't worry if you haven't gotten the idea yet, but that's something we start discussing next week. Okay, so let me stop here. And if there are any questions, I'd like to respond to that. Everything okay? All right, so I have to go to another meeting. So I see you next week and you'll see new homework problem later today. Bye.
Thank you,
Have a good
Professor.
weekend.